So I'm the last in this chain of Decadal speakers. I'm James Keane, and so I was on the Moon and Mercury panel, and I had the privilege of not only serving on that panel, but being the science champion for the endurance concept study that was performed within the Decadal survey. And so I'm going to give a really quick explanation of what this concept is. I do want to note that the full concept study report, along with every concept study report done in the Decadal survey, is publicly available. If you want another multi-hundred-page document to read, it's there for you. And while I've been going out and talking about it, I want to emphasize the large number of people, both at JPL and within the Decadal survey, and some folks outside of it, that helped with this concept study. So what is endurance? So it's a mission to the South Polacan Basin. This is my favorite picture of the moon, which is taken from a NOAA spacecraft. And here you can see South Polacan Basin as this sort of slightly darker region on the far side of the moon. As Carly gave a wonderful introduction to the basin yesterday, it is ginormous, it is ancient, and it is really important. So important that it's been prioritized in every planetary decadal survey. Why is it prioritized? This is a very quick spiel through it. The first reason is chronology. So in this plot in the top right that looks like a timeline from a Doctor Strange movie, you can see diverging hypotheses for what we think the impactor rate in the inner solar system was going back in time to about 4.5 billion years ago. And we just don't know what's happening as we go further back in time. Was there a late heavy bombardment or impact cataclysm? How old is the moon's crust? How extensive is its impact record? These sorts of things we just don't know the answer to. And it turns out that the answer is in South Polacan Basin. And why should you even care about all those squiggly lines? As mentioned in the previous talks, what's important here is everything else that's happening across the rest of the solar system at this time. Things like magma oceans and the emergence of life. So it's a very important thing to get right. The second of this sort of big science case for SPA is one of a family of giant impact basins across the solar system. And as we explore more and more of the solar system, these giant impact basins just pop up everywhere and everywhere and dominate their planets and moons in ways that we don't fully understand. In addition, as the lovely 3D ICL model on the left shows, courtesy of Jordan Kendall, giant impact basins naturally exhume large amounts of material from the deeper interior. So they provide a window into the interior structure and thermochemical evolution of a body. So SPA is wonderful, and it motivates the endurance concept, which has these objectives listed on the left. And on this synthetic view on the right, you can see SPA again, which really pops out when you look at topography. So this is a topographic map. The challenge here is to answer all the questions we want to do at SPA requires going to different places. So for example, if you wanted to get at, say, impact melt, you might want to go to the middle of the basin, things like SPACA if you're a Dan Moriarty fan. If you want to look at other impact basins to test things like the late heavy bombardment, you want to get at other large pre-Imbrium impact basins, which are shown here in blue. If you want to get at possible mantle material or deep crustal material, you might try to hunt around for high thorium anomalies, which are shown here in purple. And if you want to do anything about volcanism, you might imagine going to a volcanic deposit like the Mare deposits shown here in red. And as you'll note, while there are overlaps, there's no one place you can go to answer all of these science questions, which is why, in Carly's words, you need a sample return campaign, and that is endurance. It is a sample return campaign in one mission. The idea is to land in the middle of the basin, traverse through all of these key terrains, and get the samples you need to answer these questions and drop them off at the Artemis astronauts. Endurance is an evolution of the Intrepid pre-decadal mission concept study, which it's hard to oversell how transformative that concept was. It motivated 2 additional internal decadal survey studies, including Endurance and Inspire, which you can see here. So a total of 5 rovers in this lineage. And it opens up all sorts of new science that is very new for this decadal survey. So our rover looks a lot like the Intrepid rover. It's a quite large rover. Some of the key things, I'm not going to list through all of this, is that it is highly autonomous and it drives fast by rover standards. peaking out at 1 kilometer per hour, so still slow by astronauts doing donuts on the moon. And it has a suite of in situ instruments and a sample collection system. Here I'll show some other views. Since it's on the far side, it requires a communications relay, and we only considered an RTG power system because it's going to be driving down to the South Pole. And here it is to scale to an engineer, shiny woman, but it's just to demonstrate how large and capable this rover is. I'm speeding along to get to Q&A. Samples. So as you can see on these boxes on the side, this rover is designed to carry up to 100 kilograms of material. That 100 kilograms, we basically push the engineers to say, how much can you fit on this before we start breaking the rover? That's the number we got. And I know 100 kilograms is both exciting and scary. If you were to actually boil this down to the actual underlying requirements, you don't need 100 kilograms of rock to answer the questions we outlined. If you really pick the right samples, you might be able to do this in only a few kilograms or 10 kilograms or something like that. But this, again, this is demonstrating that with this sort of rover, you could do effectively an Apollo 17 mission across the entire basin or multiple Apollo 11s. And once you get those 100 kilograms to the astronauts at the South Pole, then there's other challenges that are going to have to be solved for this mission to succeed. We don't yet know the full architecture setup for Artemis, so it's hard to know exactly whether they could return 100 kilograms in one go, or if you need to do some sort of triage or other ways of managing your sample to get them back and do the science. There's a detailed cost estimate in the report. This is the only time in here that I'll talk about the other endurance R. The A, if you haven't gathered, stands for astronaut or Artemis. The R was a robotic sample return version, and basically the goal was to see what is the cost savings to NASA if we can leverage humans to help do the science and return the samples. Short version, you save about $1 billion. So it's very advantageous if you can do this. And this is my summary slide, which has a bunch of quotes from the Decadal survey advocating for the concept. But in short, long-range, Intrepid-style lunar rovers are game-changing and credible. Endurance does the highest priority lunar science of the last 3 Decadal surveys. And one thing that I didn't write down here, but Endurance I kind of view as sort of a cornerstone of what could be a lunar program that could live beyond this decade. I kind of hope that Endurance might just be the first of such long-range rovers that get deployed on the moon to do priority science. And with that, I'll stop, and I guess we go to Q&A.